All right, welcome back for another deep dive. You've really outdone yourself this time. You've given us a ton of material to dig through, from basic statistics all the way to deep learning.
Yeah, it's quite a bit.
So what we're going to try to do today is extract the most important points from everything you've given us, kind of like panning for gold. But instead of gold, we're looking for, those golden nuggets of knowledge, the core concepts, the connections between these fields, and how you can actually put them to work.
Right. And I think it's important to start with recognizing the overall relationship between these areas. I mean, statistics gives us the tools to understand and analyze data. Data science uses those tools to ask interesting questions and solve problems. And then machine learning and deep learning, those are the algorithms and techniques we use within data science to discover patterns, make predictions, really extract meaning from all that data.
Yeah. Okay. So let's lay the foundation with statistics. One concept that keeps popping up is the Central Limit Theorem. What makes that so important, and what does it really mean?
Well, the Central Limit Theorem, it's a really powerful concept because it tells us something amazing about averages. Even if the underlying data you're looking at is all over the place, if you take enough random samples from that data and calculate the average of each sample, those sample averages will start to form a normal distribution.
Oh, okay. So it's like those sample averages, they kind of smooth out into a bell curve.
Exactly. And that's incredibly useful because we understand the normal distribution really well. We can use it to make inferences about the whole population, even if we've only looked at a small part of it through sampling.
You mentioned sampling. Can you remind us what that is and why it's so crucial?
Right. So sampling is about choosing a smaller representative group from a larger population so you don't have to analyze everything. It's like taking a taste of soup to see if the whole pot needs more salt. There are different ways to do it, like simple random sampling, where everyone has an equal chance of being selected, or cluster sampling, where you divide the population into groups and randomly choose some of those groups.
It's like choosing the right spoonful of soup to get a good taste of the whole pot.
That's a great analogy.
So when we're analyzing these samples, we've got to be careful about errors. Now, I've always struggled with understanding type I and type 2 errors.
Yeah, that can be tricky.
Is there a way to think about them that makes it a bit more intuitive?
Okay, so imagine a smoke detector.
Okay,
A type I error, it's like the smoke detector going off when there's no fire, a false alarm.
right, got it.
You're rejecting the idea that there's no fire when there actually isn't one. A type 2 error is the opposite. There's a real fire, but the smoke detector doesn't go off.
Oh, okay, so you're failing to detect a real problem.
Exactly. And in business, a type I error might be launching a product no one wants based on bad market research, while a type 2 error could be missing out on a successful product because you didn't see its potential.
Makes sense.
Yeah.
Now let's talk about making predictions. Linear regression seems to be a fundamental tool for that.
Yeah, definitely.
What's the basic idea behind it? And how do we make sense of the p-value, the coefficient, and that r-squared value?
Okay, imagine you're trying to predict apartment prices based on their size. Linear regression tries to draw a straight line that best fits the relationship between those two variables. The line shows how the price generally changes as the size changes.
Got it.
The p-value tells you how strong the evidence is that there's actually a relationship between size and price. A very low p-value, usually less than 0.05, means the relationship is statistically significant and probably not just random chance.
Okay, so a low p-value means it's a real deal.
Right. The coefficient of the size variable, that tells you the direction and strength of the relationship. A positive coefficient means bigger apartments tend to have higher prices.
Right.
And the r-squared value, well, that tells you how much of the variation in prices you can explain with size. So an r-squared close to 1 means your model fits the data really well.
So a higher r-squared, the better our model explains what's going on.
Generally, yeah. But it's not the only thing to look at. A high r-squared doesn't automatically mean you have a great model. It's possible to get a high r-squared by including too many variables, even some that don't really make sense.
Oh, interesting. So we need to be careful about just chasing a high r-squared value.
Exactly.
Now, are there any assumptions we need to be aware of when using linear regression? Are there things that could trip us up?
Yeah, there are a few key assumptions. The relationship between the variables should be roughly linear. The errors should be independent and normally distributed, and there shouldn't be too much correlation between the independent variables. That's called multicollinearity. And the variance of the errors should be pretty consistent across different levels of the independent variables.
So we need to make sure our data kind of meets these criteria for the results to be reliable.
Exactly, yeah.
Now, what about this idea of a statistical interaction? When does that come into play?
So an interaction happens when the effect of one variable depends on the value of another variable. Think about how well a fertilizer works on crops. It might be super effective if there's enough rain, but not so much during a drought.
Oh, okay.
So the effect of the fertilizer interacts with the amount of rainfall.
I see.
And understanding these interactions is important because they show that relationships aren't always simple and straightforward.
Makes sense. Now, you mentioned selection bias earlier when talking about sampling. What are the other types of bias that we need to be aware of in data analysis?
Well, selection bias is really a broader category. It's about how the data you're working with might not be truly representative of the bigger picture. It can happen in different ways,
Hmm.
like undercoverage bias, where certain groups are missing from your sample. Think about those old landline phone surveys. They probably missed a lot of younger people who mostly use cell phones.
Right.
And then there's survivorship bias, where you only focus on those who survived a certain process, ignoring those who didn't. Like if you only study successful businesses, you might miss important lessons from the ones that failed.
So it's about remembering that what we see in our data might not be the whole story.
Exactly. And that's where a solid understanding of statistics helps you identify these biases and avoid making faulty conclusions.
Absolutely. And we talked about the normal distribution, but the materials also mentioned non-Gaussian distributions. Why are those important, especially when we're dealing with machine learning?
Well, the normal distribution, that bell curve, it's common, but it's not the only shape data can take. There are lots of other distributions out there, like the exponential distribution, often seen with waiting times, or the Poisson distribution, which is good for counting rare events. Recognizing these different shapes is crucial because some statistical tests and machine learning algorithms assume the data follows a normal distribution.
Okay, so we need to make sure we're using the right tools for the right data.
Exactly. And that's where a strong statistical foundation comes in, knowing which tools work best for different types of data.
Makes sense. Speaking of the right tools, what about the binomial probability formula? When would we use that?
The binomial probability formula is your go-to when you want to know the chances of a certain number of successes happening in a set number of tries, where each try only has two possible outcomes and the probability of success stays the same each time. Like flipping a coin, you have heads or tails. Each flip is independent, and the chance of getting heads is always the same.
Got it. It helps us figure out how likely a certain number of wins is in a series of events with two outcomes.
Exactly.
Now, what about long versus wide data? What's the difference and why does it matter?
Think about it this way. In wide format, each thing you're measuring, like a customer, gets its own row, and different measurements about that customer are spread across columns. So if you're tracking purchases over time, each customer would have columns for month 1 purchases, month 2 purchases, and so on. But in long format, every single measurement gets its own row, even for the same customer. So you'd have multiple rows for each customer with one column for the customer ID, another for the month, and another for the number of purchases.
So wide is like a spreadsheet where each row is a snapshot of a customer, and long is more like a database where each row is a specific observation.
That's a good way to put it.
Huh.
And the format you choose depends on the type of analysis you want to do. Long format is often better for statistical modeling, especially with repeated measures over time.
Got it. Now, we touched on the normal distribution earlier. Can we just recap its key characteristics?
Sure. The normal distribution, that classic bell curve, it's symmetrical, meaning it looks the same on both sides of the middle. It's unimodal, so has one peak in the center, and the mean, median, and mode, they all line up right at that peak.
So it's all about that balance and symmetry around the average.
Yeah.
Now, correlation and covariance, they both describe how variables move together. But what's the practical difference for us?
They both tell you about the relationship, but in different ways. Covariance just shows you the direction. Do the variables tend to increase or decrease together? But it doesn't really tell you how strong that relationship is because it depends on the scales of the variables.
Okay.
Correlation fixes that by standardizing the measure. It gives you a value between 1 of 1 and +1. A correlation close to +1 means a strong positive relationship, close to mono and on means a strong negative relationship, and close to 0 means there's not much of a relationship at all.
So correlation gives us a more interpretable number to judge the strength and direction of the relationship.
That's right.
What about point estimates versus confidence intervals? When should we be thinking in terms of a single value, and when do we need a range?
Well, a point estimate is just a single best guess at a population value based on your sample. Like if you calculate the average height of everyone in your sample, that average is a point estimate for the true average height of the whole population.
Right.
But it doesn't tell you how much uncertainty there is around that estimate. A confidence interval gives you a range of values that you're reasonably confident contains the true population value. So a 95% confidence interval for average height might be 5'8" to 5'10". That means we're 95% sure the true average height falls somewhere in that range.
So it gives us a sense of how much we can trust that single point estimate.
Exactly. It acknowledges the uncertainty inherent in using a sample to represent a whole population.
Now, A/B testing, it's everywhere these days. Can you remind us what its main goal is?
A/B testing is all about comparing two versions of something, like a web page or an ad, to see which one performs better. You show version A to one group and version B to another, then see which one leads to more clicks, sales, or whatever your goal is.
It's like a controlled experiment.
Yeah.
And the p-value comes up here again, right? What does it tell us in the context of A/B testing?
The p-value helps us decide if the difference we see between version A and B is real or just due to random chance. We set a threshold, usually 0.05, and if the p-value is below that, it suggests there's a genuine difference.
So a low p-value means we're more confident that one version is truly better than the other.
Exactly.
Now, I saw some interesting probability puzzles in the materials. What was the point of the shooting star problem?
That one was a good example of how to calculate the probability of something happening at least once over a period of time. Sometimes it's easier to calculate the probability of it not happening at all and then subtract that from 1 and 6.
It's like flipping the problem around.
Yeah.
And the dice problem, rolling a 6-sided die to get a random number between 1 and 7.
Yeah.
What was the takeaway there?
That one showed how you can expand the range of outcomes from a limited random source. By rolling the die multiple times and combining the results in a specific way, you can create a new set of equally likely outcomes that map to the numbers 1 through 7.
It's about being creative with your randomness.
Yeah.
Now, the two children problem, that was a classic example of conditional probability, right?
Yeah.
What was the key point there?
That problem shows how knowing some additional information can change the probabilities. In this case, knowing that at least one child is a girl changes the probability that the other child is also a girl.
It's about updating our beliefs based on new information.
Exactly.
And the coin selection problem, that felt like a good illustration of Bayesian reasoning.
Right. We start with an initial belief about which coin was chosen, then we update that belief as we get more data, in this case, the results of the coin flips. That's the essence of Bayesian inference.
It's a formal way of incorporating new evidence into our understanding.
Precisely.
Now, what about statistical power? What does that tell us?
Statistical power is the probability that a test will correctly detect a real effect. It's like if someone actually has a disease, how likely is the test to correctly identify it?
So higher power means fewer misdiagnoses.
Yep.
And resampling. Why do we use techniques like bootstrapping?
Resampling methods are great for understanding how much uncertainty there is around our estimates. By repeatedly drawing samples from our original data, we can create a bunch of virtual data sets and see how much our results vary across them. This helps us build confidence intervals and test hypotheses in a more robust way.
It's like creating a virtual lab to run multiple experiments.
Exactly.
Now, overfitting and underfitting, those are crucial concepts in machine learning. Can we clarify the difference and why they're both bad?
Overfitting happens when your model learns the training data too well, including all the quirks and noise. It does great on the training data, but fails on new data because it hasn't learned the general patterns.
It's like memorizing the answers instead of understanding the concepts.
Yeah, a good analogy. Underfitting is the opposite. The model is too simple and misses the important patterns, so it does poorly on both the training data and new data.
So one is too complex, one is too simple, and neither generalizes well.
Right.
And how do we deal with these problems?
For overfitting, techniques like cross-validation can help by giving us a more realistic estimate of how well the model will do on new data. We can also use regularization, which adds a penalty for complexity to the model's training process, encouraging it to be simpler. For underfitting, we might need a more complex model or better features.
It's about finding the right balance.
Yeah.
Now, you mentioned regularization as a way to prevent overfitting. How does that actually work?
Regularization is basically adding a constraint to the model's learning process. It penalizes complexity by adding a term to the function the model is trying to minimize during training. This encourages the model to learn simpler relationships, which tend to generalize better.
It's like telling the model, keep it simple, stupid.
Kinda, yeah.
Now, the law of large numbers, that sounds pretty fundamental. What's the main idea?
It basically says that as you get more and more data, your sample statistics, like the average, will get closer and closer to the true population values. More data means a more reliable picture of reality.
So bigger data sets generally lead to better insights. What about confounding variables? Why do we need to worry about those?
A confounding variable is like a hidden factor that influences both the thing you're studying and the outcome you're measuring. It can create a false appearance of a relationship between them.
Can you give an example?
Sure. Let's say you find that ice cream sales and crime rates tend to increase together. You might think, wow, ice cream causes crime. But it's more likely that a third factor, like hot weather, is driving both. More people eat ice cream when it's hot, and more crime happens when people are out and about in warmer weather.
So we need to be careful about jumping to conclusions about cause and effect.
Exactly. Confounding variables can really trip you up if you're not careful.
We already discussed selection bias, but the materials also listed undercoverage bias and survivorship bias. Can you elaborate on those?
Undercoverage bias is when certain groups are missing from your data. Like I said before, those landline phone surveys might underrepresent younger people who mostly use cell phones. Survivorship bias is when you only look at the successes and ignore the failures, like studying only successful businesses without considering the ones that went bankrupt.
So we need to make sure we're getting a complete picture.
Yes.
Now, the ROC curve, that's a tool for evaluating classification models.
Yep. It helps visualize the trade-off between correctly identifying positives and incorrectly identifying negatives as positives. A good model will have a curve that bows up towards the top left corner, indicating a high true positive rate and a low false positive rate.
So it helps us see how well the model balances those two types of errors.
Precisely.
And when we're working with text data, TF-IDF vectorization comes up a lot. What's that all about?
TF-IDF is a way to convert text into numbers that machine learning algorithms can understand. It gives higher weights to words that are frequent in a specific document but rare across a collection of documents.
So it helps identify the key words that are characteristic of a particular document.
Yeah.
And finally, why is softmax often used in neural networks, especially for classification tasks with more than two categories?
Softmax is used as the last layer in a neural network to turn the network's raw outputs into probabilities for each class. This makes it easy to interpret the network's prediction as a measure of confidence for each possible outcome.
So it gives us a probability distribution over the different classes.
That's right.
Okay, that covers a lot of the statistical foundations. Let's shift gears and talk about data science itself. How would you define it, and how is it different from traditional statistics?
Data science is a multidisciplinary field that combines statistics, computer science, domain expertise, and more to extract knowledge and insights from data. It's not just about understanding the past, but also about predicting the future and making data-driven decisions.
So it's more applied and future-oriented.
Yeah, it's about using data to solve real-world problems.
And within data science, there's this key distinction between supervised and unsupervised learning. Can you remind us what those are all about?
Supervised learning is like teaching a machine with labeled examples. You give it data where you already know the correct answers, and it learns to predict those answers for new data. Unsupervised learning is more about letting the machine explore the data and find patterns on its own without any predefined labels.
So supervised is about prediction with known answers, and unsupervised is about discovering hidden patterns.
Exactly.
And selection bias, it can pop up in data science projects too. Right.
Definitely. It's not just about the initial sampling. You also have to consider things like time interval bias, where the period you're analyzing might not be representative, or data availability bias, where you're limited by what data you have access to. And then there's attrition bias, where people or data points drop out over time in a way that might skew the results.
So lots of potential pitfalls to watch out for.
That's why a solid understanding of these biases is so important.
Absolutely. Now, the bias-variance trade-off, that's a core concept in machine learning. What is that all about?
It's about finding the right balance between two types of errors. Bias is about the error that comes from using a model that's too simple to capture the complexity of the data. Variance is about the error that comes from a model that's too sensitive to the noise in the data.
So one is about oversimplifying, the other is about overfitting.
Right. And as you increase a model's complexity, you typically decrease bias, but increase variance, and vice versa. It's a delicate balancing act.
Got it. Now, how do we evaluate how well a classification model is performing? The confusion matrix seems to be a key tool.
Yeah, a confusion matrix is a table that shows how many predictions the model got right and wrong for each class. It tells you how many true positives, true negatives, false positives, and false negatives there are.
And from that, we can calculate things like error rate and accuracy, right?
Exactly. Error rate is just the proportion of incorrect predictions, and accuracy is the proportion of correct predictions. But remember, accuracy can be misleading, especially if the classes are imbalanced.
Right, it's not the whole story.
Nope. That's why we also look at other metrics like sensitivity, specificity, precision, and the F-score, which give us a more nuanced view of the model's performance.
So they give us a more complete picture of where the model is doing well and where it's struggling.
That's right.
Now, let's zoom in on machine learning itself. What's the essence of this field?
Machine learning is all about building algorithms that can learn from data without being explicitly programmed. Instead of writing specific rules for every scenario, we give the machine data and let it figure out the patterns and make predictions.
It's like teaching a machine to think for itself.
In a way, yeah.
And we talked about supervised and unsupervised learning as two main types. Could you give us some more concrete examples of where these are used?
For supervised learning, think about spam filtering for emails. The algorithm learns from labeled examples of spam and non-spam emails to predict which category a new email falls into.
Okay, so that's supervised because we're giving the algorithm labeled data to learn from.
Right. And for unsupervised learning, think about customer segmentation. An algorithm might group customers based on their purchasing behavior without knowing beforehand what those groups should be.
So it's about finding hidden structures in the data.
Exactly.
Now, the sources mentioned a bunch of different classification algorithms. Can you give us a quick rundown of some of the key ones?
Sure. Some of the common ones include logistic regression, which predicts the probability of a binary outcome; naive Bayes, which is a probabilistic classifier based on Bayes' theorem; support vector machines, which find the optimal hyperplane to separate classes; decision trees, which use a tree-like structure to make decisions; k-nearest neighbors, which classifies data points based on their closest neighbors; and ensemble methods like random forests, which combine multiple decision trees.
Okay, lots of different tools for different jobs.
Absolutely.
We briefly touched on naive Bayes earlier. Why is it called naive?
It's called naive because it makes the simplifying assumption that all the features are independent of each other, which is often not true in the real world.
So it sacrifices realism for simplicity.
But it can still be surprisingly effective in some cases.
And support vector machines, those seem pretty powerful. How do they work?
SVMs try to find the best hyperplane that separates data points of different classes in a high-dimensional space. The best hyperplane is the one that maximizes the margin, or the distance between the hyperplane and the nearest data points from each class.
So it's all about finding the optimal dividing line.
Yes. And by using different kernels, which are like functions that transform the data, SVMs can handle even non-linear relationships between the variables.
Okay, so kernels give them more flexibility.
That's right.
Now, decision trees, those seem pretty intuitive. How do they make a classification decision?
They work by creating a tree-like structure where each node represents a test on a feature. You start at the root node and follow the branches based on the values of your features until you reach a leaf node, which gives you the prediction.
It's like a flowchart.
Yeah, a good way to think about it. And the tree is built by recursively splitting the data based on the features that best separate the classes.
And entropy and information gain, those are important concepts in building the tree, right?
Yes. Entropy measures the impurity or disorder in a set of data points. A high entropy means the data is mixed across different classes. Information gain measures the reduction in entropy achieved by splitting the data on a particular feature. The algorithm tries to choose features that maximize information gain, making each split as informative as possible.
So it's all about finding the best splits to create the most homogeneous groups.
That's right.
And pruning, what's that for?
Pruning is like trimming the tree to prevent overfitting. It involves removing branches or subtrees that don't add much predictive power or might be based on spurious patterns in the data.
So it's about simplifying the tree to make it more robust.
Exactly.
Now, what about logistic regression? How does that work for classification?
Logistic regression is a linear model that uses a sigmoid function to predict the probability that a data point belongs to a particular class. It's commonly used for binary classification problems, but can be extended to handle multiple classes as well.
So it outputs a probability, not just a yes or no.
Right. And the sigmoid function squashes the output between 0 and 1, giving you a probability interpretation.
Got it. And what about linear regression, which we discussed earlier? How is it used specifically as a machine learning technique?
Linear regression, as an ML technique, is about finding the best fitting line that predicts a continuous target variable based on one or more predictor variables. It's commonly used for predicting things like house prices, stock prices, or sales figures.
So it's about finding a linear relationship between variables to make predictions.
Yes,
Are there any drawbacks to using linear models like logistic and linear regression?
of course. One major drawback is that they assume a linear relationship between the variables, which might not always be true. They're also not great for dealing with count data or binary outcomes, though logistic regression can be used for binary classification with some adjustments. And they can be prone to overfitting, especially when dealing with high-dimensional data.
So they're not always the best tool for the job.
That's right. But they're often a good starting point and can be very effective in the right situations.
Now, we should clarify the difference between regression and classification in machine learning.
Absolutely. Regression tasks involve predicting a continuous output, like a price or a temperature. Classification tasks involve predicting a discrete output, like a category or a label.
So regression predicts numbers
Yeah.
and classification predicts categories.
That's a good way to remember it.
Now, what about recommender systems? What are they all about, and what are some common techniques used in them?
Recommender systems are designed to predict user preferences and make recommendations based on those preferences. They're used everywhere these days, from suggesting products on Amazon to recommending movies on Netflix. One common technique is collaborative filtering, which leverages the behavior and preferences of similar users to make recommendations.
So if I like the same movies as you, the system might recommend movies that you liked but I haven't seen yet.
Exactly. And there's content-based filtering, which focuses on the characteristics of the items themselves to make recommendations. For example, if you've watched a lot of action movies, the system might recommend other action movies.
So it's about finding patterns in user behavior and item characteristics to make personalized recommendations.
That's right.
Now, what about outlier values? How should we handle those in our analysis?
Outliers can be tricky. They can be genuine data points that represent rare events, or they can be errors in data entry or measurement. The key is to understand why they're there and how they might impact your analysis. Sometimes it makes sense to remove outliers if they're clearly errors, but other times it's important to keep them in. You might also consider replacing outliers with more reasonable values, or using robust statistical methods that are less sensitive to outliers.
So it's not a one-size-fits-all approach. We need to carefully consider the context.
Exactly.
Now, what are the typical steps involved in an analytics project?
A typical analytics project starts with understanding the business problem you're trying to solve. Then you move on to data exploration, where you get familiar with the data, clean it up, and look for patterns. Then comes data preparation, where you transform the data into a format suitable for modeling. Next is the modeling phase, where you choose and train a model to solve your problem. Then you evaluate the model's performance and fine-tune it as needed. Finally, you deploy the model and monitor its performance over time.
So it's a structured process from problem definition to deployment and monitoring.
Yeah, and it's important to remember that it's often an iterative process. You might need to go back and forth between different steps as you learn more about the data and the problem.
Makes sense.
Yeah.
Now, what about missing values? How should we deal with those?
Missing values are a common problem in real-world datasets. First, try to understand why the values are missing. Is it random, or is there a pattern? If it's random, you might be able to impute the missing values with the mean or median of the non-missing values. If there's a pattern, you might need a more sophisticated imputation technique. You could also consider dropping variables with too many missing values or assigning default values.
So again, it depends on the context and the nature of the missingness.
Exactly.
Now, we talked about some general sampling techniques earlier. Are there any other specific sampling methods we should be aware of?
Sure. Cluster sampling, which we mentioned earlier, involves dividing the population into clusters and randomly selecting some of those clusters to study. Systematic sampling involves selecting every nth element from a list. For example, you might choose every 10th person on a customer list.
So different ways to get a representative sample.
Yes.
Now, eigenvectors and eigenvalues, those are terms that come up a lot in linear algebra. What are those all about?
They're basically about understanding how a linear transformation changes the direction and magnitude of vectors. Eigenvectors are special vectors that don't change their direction under the transformation. They just get scaled by a factor. That factor is the eigenvalue.
So they're about how vectors get stretched or shrunk.
Yeah, in a way, and they're used in a lot of different applications, from dimensionality reduction to image processing.
Got it. Now, we talked about false positives and false negatives in the context of the confusion matrix. Are there situations where one type of error is more important than the other?
Definitely. In medical diagnosis, a false negative, missing a real disease, is usually much worse than a false positive, diagnosing someone with a disease they don't have. But in security, a false positive, flagging a harmless event as a threat, might be preferable to a false negative, missing a real threat.
So it depends on the consequences of each type of error.
Exactly. And sometimes both errors are equally important, like in loan approval, where you don't want to lose good customers or give loans to bad ones.
Makes sense. Now, we also talked about training and testing sets in machine learning. What about validation sets? What role do they play?
A validation set is a subset of the training data that you use to tune the model's parameters and prevent overfitting. You train the model on the training set, evaluate its performance on the validation set, and adjust the parameters accordingly. Then, once you're satisfied with the model's performance on the validation set, you do a final evaluation on the test set, which is completely unseen data.
So the validation set is like a dress rehearsal before the final performance.
Yeah, a good analogy.
Now, cross-validation, that's another important technique for evaluating models. What is that all?